This lecture is about double replacement reactions, and there are three types of double replacement reactions that we'll go over. Precipitation reactions, which are the most common of the three. Neutralization reactions, also called acid-base reactions. And gas evolving reactions. It's really important to understand solubility of ionic compounds, which we covered in the last lecture, before we get into precipitation reactions. So let me just review quickly. When an ionic compound dissolves in water, remember that two things happen. Dissociation of the intact ionic compound into the individual ions, the cation and the anion, and then solvation by the water molecules. Just a reminder, not all ionic compounds dissolve. Some of them are insoluble. So in the last lecture, I had a solubility chart. Make sure that you print that out or write it and start memorizing which ionics dissolve and which do not. And here it is as a reminder. This doesn't look it's not as complicated as it looks. Just real briefly, even though I know I went over this in class. If an ionic compound contains any of the group 1A metals, that's lithium, sodium, potassium, it is automatically soluble. Okay, so sodium chloride, lithium chloride, anything that has a group 1 metal in it is soluble. Nitrates are soluble. That's ionic compounds that have NO3, so that would be, let's do one like magnesium nitrate. Okay. These are called acetates. They are soluble. If the ionic compound contains a halide from group 7A as the anion, they are soluble. Okay, so magnesium chloride, aluminum chloride, those are all soluble. There are some exceptions for the halides. If the halide has an anion that's silver, mercury, or lead, it is not soluble. So, for example, if we have silver chloride, that's not soluble because silver is one of the exceptions. If we have mercuric iodide, that's not soluble. Mercury is one of the exceptions. All right, and then sulfates tend to be soluble. Now, you can make some summaries about the ionic compounds that are not soluble. If an ionic compound has OH, it is typically not soluble. So magnesium hydroxide, for example, is not soluble. Same thing with sulfide. Magnesium sulfide is not soluble. Carbonates and phosphates are also not soluble. There are some exceptions. The exceptions over on the right-hand side at the bottom make it soluble. So while, let's see, I should probably, no, that won't, no, it's not what I meant to do. Okay, so while, let's do magnesium hydroxide is not soluble because it has a hydroxide in it. If the cation is something from group 1A, so let's say lithium hydroxide, it is soluble. Okay, so just go through, make sure you interpret this chart. I would either print it out or write it on a note card and start committing it to memory. All right, so the first double replacement reaction is the precipitation reactions. What is a precipitate? A precipitate is an insoluble solid. Okay, a precipitate is an insoluble solid. So it's something that you add it to water and it just drops to the bottom, doesn't dissolve. In a precipitation reaction, you have two ionic compounds that react together, and when they react, they make a product that is insoluble in water. So that probably makes no sense at this point, so let's go on. I'll give you some examples. So here's kind of a conceptual example. Again, precipitation reactions are always between two ionic compounds. So make sure you know how to identify ionics. So in this case, potassium iodide and lead nitrate, lead 2 nitrate. When you add them together, notice that there's AQ next to each of them, which means dissolved in water. So both of these ionic compounds are soluble in water. When you mix them together, there is a chemical reaction, and the products are potassium nitrate, which is soluble because it has a group 1 metal, and plus it's a nitrate, and lead iodide, which is one of the insoluble ionic compounds. Because it's insoluble, it is called a precipitate. Okay? So when you mix these two things together, you can actually see a solid forming in solution, and here it is. Okay? So lead iodide is kind of famous because it's a yellow solid, so it's pretty obvious. Now let's look at a molecular level what a double replacement reaction is. Remember that the precipitation reaction is a type of double replacement reaction. So in a double replacement reaction, you have two reactants. Okay, they're both ionic compounds. So silver is the cation in one, potassium is the cation in the other, and nitrate is the anion in the first one, and chloride is the anion in the second. So what happens in a double replacement reaction is these ionic compounds switch partners. So the silver cation ends up with a new anion, in this case chloride, and the potassium cation ends up with a new anion, which in this case is nitrate. So the products we end up getting are silver chloride and potassium nitrate. Now, an easier way to remember that, I usually circle the cations and the anions, then the two outer ions end up together, silver and chlorine, and the two inner ions end up together, potassium nitrate. Remember that the metal is always shown first in the formula. So when you combine the inner ones, don't write it as NO3K or you'll get it wrong. Put the metal, the potassium, first. All right, so if it is a precipitation reaction, one of the products formed will be insoluble. So you have to know the solubility rules, and potassium nitrate soluble because it has a group 1A metal plus a nitrate anion, and both of those make it soluble. Silver chloride is not soluble. Silver is one of the exceptions that turn chloride insoluble. Notice the S. Okay, S stands for solid, and what that means is insoluble. So there we go, it's a precipitation reaction. If you mix two ionic compounds together, and let's write out what the product would be here if they switched partners. Remember, combine the two outer ones, so that would be potassium chloride, and then combine the two inner ions, which would be sodium and iodine. If you look up the solubility for both these potential products, they're both soluble because they both contain a group 1A cation. So if you mix two ionic compounds together in an attempt to do a double replacement, if all products formed are soluble, that is no reaction. You have to remember that on your next test or quiz. Okay, you have got to check the products. If one of them, at least one of them, is not soluble, well, let me put it the other way. If they're all soluble, you write no reaction. Now, the trickier, the harder part is what I will often give you are the reactants, the two ionic compounds that are reacting. I will say, what are the products? So this is where you should be really alert, really paying attention, taking notes, whatever, because this is a tricky part. So here's a list of rules which you can print out or write down for future reference. So of course, separate the cation and anion if it's a soluble compound. Then swap partners. In other words, each cation ends up with a different anion partner. Now, this step, this should be step 3, shouldn't it? This step is the one that students mess up on. So let's imagine that I had magnesium chloride plus silver nitrate. Okay. So what if I said, okay, what are the products for that? So remember, you're going to combine the outer ions together. So magnesium and nitrate are together. But guess what? In order to know the correct formula of magnesium nitrate, you can't just necessarily put them together in a 1-to-1 ratio because it depends on their charge. Remember, magnesium has a charge of 2+. Nitrate is a polyatomic with a charge of -1. So what is the formula for magnesium nitrate? It is MgNO3 2. Okay? So you have to do that for every product you form. You've got to assign charges and crisscross. What is the other product? The other product is combining the inner ions, okay, which in this case are silver and chlorine. You need to crisscross or assign charges. Metals go first, so I'm going to put silver there. Silver always has a charge of +1. Chlorine has a charge of -1. So when they combine, it's in a 1-to-1 ratio to make silver chloride. Okay, so this step is a particularly tough one for students. All right, once you have written out the potential products, and they're magnesium nitrate and silver chloride, you have to refer to the solubility rules. Remember, in order for this reaction to occur, at least one of these products has to be insoluble or precipitate. So let's look at the two I have here. Magnesium nitrate, is it soluble? Yes, so you'd put aqueous by it because it has the nitrate group. Nitrates are soluble. Is the other product, silver chloride, soluble? No. It is insoluble, so you show that with the S in parentheses. It is they precipitate. PPT is the abbreviation for precipitate. So here's a visual showing you those steps. Let's say you have an aqueous solution of potassium iodide. Now remember, if you have a soluble ionic compound, they dissociate, okay? So you have potassium cations and iodine anions. So that's what this beaker picture is. And let's say you're going to combine that with lead nitrate, which is also another soluble ionic. So in there you have lead ions and nitrate ions solvated. And so what are your potential products? Okay, so far we have potassium iodide reacting or mixed with lead nitrate. Okay, now remember, combine the outer ions, so you're combining potassium and nitrate, and you want to crisscross charges. Potassium has a charge of +1, nitrate is a polyatomic with a charge of -1, so the formula for potassium nitrate, KNO3. Then you combine the inner ions, making sure to put the metal first. Lead, in this case, has a charge of +2. And you combine it with iodine, which has a charge of -1. Crisscross, and the formula for lead iodide is PbI 2. Then you look at the two potential products formed and see if one of them is a precipitate. Potassium nitrate is not, it's soluble, so you put AQ because it has a group 1A metal, plus it's a nitrate, so it's super soluble. Lead 2 iodide is an insoluble precipitate because lead is one of the exceptions that make halides insoluble. So at this point, what is important that you need to be able to do? You need to be able to write formulas for ionic compounds by assigning charges and crisscross. You need to be able to go through the process of predicting products from a double replacement reaction. And you need to be able to tell the solubilities of ionic compounds. All right, so now it goes into depth a further step down. Here is a double replacement reaction. Silver chloride's the precipitate. I know that because of the S next to it. And there are 3 different types of chemical equations you're expected to be able to write. The regular one that we're used to is called the molecular equation. Just shows all of the ionic compounds intact. And so that's pretty straightforward. Then you have something called an ionic equation. And more thoroughly, the complete ionic equation. So what you do with that is you dissociate soluble ionic compounds. You dissociate soluble ionic compounds. So we started with, in this case, silver nitrate. We mixed it with potassium chloride. And then the products were silver chloride and potassium nitrate. All right, so you have to ask yourself, is it soluble? Yes, silver nitrate is. If it's soluble, when you put it in water, it's going to dissociate. So that's what we've done here. Same thing with KCl, potassium chloride. It is soluble, so you separate it into its ions. Now you have to evaluate the solubility of the products. Silver chloride is not soluble. It is a precipitate. So it doesn't dissolve, it doesn't dissociate into the ions, you keep it intact. The other product, which is potassium nitrate, is soluble, so you separate it into its ions. So this is the total or complete ionic equation. Now what you do is the third type of equation, you are going to cross out the ions that are identical on both sides of the arrow. So look for a minute at this. Both sides have potassium, both sides have nitrate, okay? They have to be identical, okay? And what are you left with when you cross out the potassium and the nitrates? That is called the net ionic equation. All right, so I've just reenacted it here. So the net ionic equation shows you what's actually going on in the reaction. So we have all these ions floating around, not really participating in the reaction, but what's actually reacting and making a different species is silver cation with chloride anion because they're making the precipitate. So in 90% of the cases, when you write a net ionic, it's actually going to show you the precipitate that forms because that's what's really reacting. Okay. So now what about those ions we crossed out? All of the ions that get crossed out are called spectator ions because they never combine to make a new solid. They remain as individual ions, so they don't participate in the reaction itself. So here is a set of rules for writing a net ionic equation, and you can pretty much count on that being one of the free response questions. So you start out by writing a regular balanced chemical equation for the reaction. Then you have to be able to figure out the solubilities of all the reactants and all the products. Dissociate or separate, let's say soluble ionics. It's going to separate all the soluble ionics. And you're going to leave pure solids and pure liquids intact, or you're not going to separate them. Also, if you have any type of covalent compound, remember you don't separate those. Then you cross out anything that's exactly the same on the reactant side and the product side. Remember, those are called spectator ions. And what's left over is the net ionic equation. So let's do a couple of examples. Here is a molecular equation. I was nice and told you what was soluble and what is a precipitate. So what if I said, okay, write out the total ionic and the net ionic equations. Everything that's soluble gets separated into the ions. Remember to write the quantity. This tells us we have 2 potassium ions. Subscripts become coefficients. Keep the polyatomic ion intact. Now, if there's a coefficient in the balanced reaction, the coefficient applies to both ions. So this means you have 2 silver cations and you also have 2 nitrates. You have to know, when you separate, you've got to know the charge of everything, all right? Now let's look at the products. We have this potassium nitrate is soluble, so we have to separate it. We have 2 potassium, and we also have 2 nitrates. Look at the final product, silver sulfate. Silver sulfate is a solid, it's the precipitate, so you do not separate it. And let's cross out the spectator ions, potassium and nitrate. So what we're left with is 2 silver combine with 1 sulfate to give us silver sulfate. This is your net ionic. Okay, you do this. And I'm still noticing several of you that start a little bit, but within a minute or two you're peeking at the answer. I know I may be on my soapbox here, but I'm telling you, if you don't make yourself agonize and make mistakes, you're not going to learn very well. So really make yourself go through the process on your own here. And then I will give you the answer on the next slide. All right, so I was nice here again and told you whether things are soluble or not. Now, this one's a little different, so if you made mistakes, don't worry about it. If it is a soluble ionic compound, you dissociate it, okay? So we have 2 sodium cations and 1 carbonate. And now this is a little different. This is a strong acid, and you may remember in lecture when I said there's 7 strong acids you need to memorize and 8 strong bases. If you have a strong acid or a strong base, they dissociate. You treat them like ionics even though they're really covalent. So that is a strong acid. It gives us 2 hydrogen ions. Acids always dissociate into a hydrogen ion and then what's left over, and 2 chloride. Let's look at the product now. Sodium chloride is soluble, so we have 2 sodium and 2 chloride. Now look carefully. You do not dissociate these 2. Why? They are covalently bonded molecules, okay? They're all nonmetals. There's no metal in either one of them. Covalents do not contain ions and therefore do not dissociate, okay? So you have to leave them intact. Cross out the spectator ions. What do we have the same on both sides? It's a little bit odd this time. The only thing that's the same on both sides are the chloride ions. So everything else gets carried over to the net ionic. I take it back. Sodium ions get canceled. Okay, so what we're left with is carbonate reacts with hydrogen ions to give us carbon dioxide and water. So here is the net ionic at the bottom. If I asked you a question, which I will, multiple choice, and said, what are the spectator ions? Maybe all I would give you is a molecular equation. What are the spectator ions? You'd have to go through this process, and then you would say, okay, let's see, spectator ions, we crossed out sodium, and we crossed out chloride. So those are the spectator ions. You may want to take a break at this point. Precipitation are by far the most involved of the three double replacement because you have to take into account solubility rules. But acid-base and gas evolution reactions are two other types. They're not as common, they're not quite as complex. So acid-base reactions, also called neutralization reactions, we'll talk about those first. So just a reminder, you need to be able to identify what an acid is and what a base is. An acid will start with hydrogen, and a base will tend, most of the time, have an OH group on it. So if you have an acid and a base, let's say hydrochloric acid and sodium hydroxide, it's actually a type of double replacement reaction. Acid-base reactions are a type of double replacement reaction. Let's look at why. The cation for an acid, remember, is hydrogen ion. Bases are typically just ionic compounds, so sodium is the cation. The anions are chloride and hydroxide. Follow the same rules we always have for double replacement. So the two outer ions end up together. So this is the most important part. I want you to pay attention. You have H plus and OH minus. Guess what those make? Water. So when you have an acid-base reaction or a neutralization reaction, water will always be one of your products. Okay? Water will always be one of your products because the acid will have hydrogen ions, the base will have hydroxides, so one of the products will always be H2O. The other product is the inner ions combining, and that is sodium and chloride. They combine to give you sodium chloride. So in the majority of cases, when you have an acid-base reaction, the products are a salt, which is a nickname for ionic compound, and water. Okay, so this is acetic acid. It's what's in vinegar. And I just want to point out, it's weird. Remember I said most acids, you show the hydrogen first. A lot of people write acetic acid with the hydrogen at the end. But you could write it. You'll often see acetic acid that looks like H3O2. So this is another way where you just kind of add up the atoms, but it's more obvious that it's an acid that way. So anyway, water and a salt. Here's a problem that I love. See if you can figure this out on your own before you go to the next page. What is the net ionic equation when you react a strong acid with a strong base? Remember what the definitions are for strong acid and strong base? That means that they dissociate 100% into the individual ions. Okay. So HCl is a strong acid, NaOH is a strong base, and so the products, they're an acid-base reaction, they're also double replacement, so the products are what we talked about. Water is one of the products, and the other product is NaCl. So this is the molecular equation. Now I want you to write or figure out what the net ionic equation is for this reaction. You'll have to go through the total ionic and cross out the spectator ions. You might be surprised. It's kind of cool. So put the video on pause, see if you can do it yourself first. In case you didn't jot down the strong acids and base from the last lecture, here they are again. All right, let's see how you did. Remember, anything that's soluble, well, strong acids get dissociated and strong bases get dissociated. So I dissociate both reactants into cation and anion. We know sodium chloride is soluble, so we separate it. Water is a covalently bonded compound, so it does not contain ions and does not dissociate. Let's cross out our spectator ions. Okay, sodium shows up on both sides of the arrow, chloride shows up. When we rewrite, what do we have for our net ionic? The production of water. So now, hopefully, you can see why an acid-base reaction is called a neutralization reaction, because the acid and the base basically destroy each other, and all you're left with is water, which is neutral. Here's one for you to do. This is reaction of an acid with a base, type of double replacement. So I want you to go through the steps of predicting the products. So remember, you're going to combine the outer ions and the inner ions. You've got assigned charges and crisscross. And so first you're going to get the molecular equation. I want you to go ahead and do that. Then if you're comfortable, figure out the net ionic equation. This is a challenge. You may have to flip back to your notes, but see if you can do it. All right, so here we go. One of the products is always going to be water, so I'm just going to write that. Now, don't get thrown off. Some of the students go, okay, there's hydrogen, there's hydroxide, but I have 2 hydroxide. Don't give me some funky product like O2H2H or something. Just write water, okay? All the different numbers and amounts of atoms will straighten out when you balance the reaction. All right, so what is the other product? Remember, you combine the inner ions. You remember to put the metal first, and you have to crisscross charges. So barium is in group 2A, so as an ion it has a charge of 2+. It's combining with fluoride, which when it's an ion has a charge of -1. So the formula for barium fluoride is BAF2. So that is your other product, BAF2. Now, in order to write the total ionic equation, you need to know the solubility of each reactant and each product. Before we talk about solubility, though, I just realized the reaction is not balanced. So let's go ahead and balance it. I'm going to start with the metals, which is barium. They're already balanced. I cannot balance OH as a polyatomic because it does not stay intact as OH. So I have to balance them as individual oxygen and hydrogen atoms. I'm going to do the fluorine next. I have 2 fluorine on the product side and only 1 on the reactant side, so I'm going to put a 2 there. Now I'm supposed to do oxygen last, so I'm going to do hydrogen right now. How many hydrogen do I have on the reactant side? Well, I have 2 from the HF, and I have 2 more from the barium hydroxide. So I have a total of 4 hydrogen on the reactant side. How many do I have on the product side? So far, just 2. How do I get 4 hydrogen in the product? By putting a 2 in front of H2O. So the reaction's balanced. Now I need to decide on solubilities. Actually, if you're talking about an acid or a base, you need to determine whether they are strong or weak. Strong acids and base dissociate into the ions. Weak ones are kept intact. So is HF one of the strong acids? No, which means it's a weak acid, which means we have to keep it intact or together in our reaction. Barium hydroxide, that is a base. Is it one of the strong bases? Yes, it is. So we dissociate strong bases and acids. So we have barium cation, we have 2 hydroxides. There's 2 here. All right, let's move on to products. Barium fluoride. Is that soluble? Fluorides in general are not soluble. Of course, if they're combined with a metal from group 1A, they would be, but barium is from group 2A. So that is not very soluble. So we're going to keep that intact and call it S for solid. And finally, water. Water is a covalently bonded compound. It never separates. So we don't have much of an ionic reaction here, do we? We've made a precipitate and we've made a covalently bonded compound. So there are actually no spectator ions in this, nothing to cancel out, and the total ionic equals the net ionic. That's kind of unusual. That won't happen real often. The third and last type of double replacement is gas evolving. And so in this case, again, you start with 2 ionic type compounds that switch partners. And hopefully by now you could predict the products. And in a gas evolving reaction, so let me just summarize these. In a precipitation reaction, the driving force for the double replacement is formation of an insoluble ionic. I can't write. Okay. In an acid-base or neutralization reaction, the driving force is formation of water, which is a covalent compound. And in gas evolving reactions, the driving force is formation of a gas. Gases are also covalent. Okay, covalents don't separate, and so that's going to be the driving force for the gas. When I say driving force, GroupMe is going nuts. I'm getting GroupMe alerts. When I say driving force, what am I talking about? Well, if you do a double replacement reaction and you end up with 2 soluble ionic compounds, so you don't make water, you don't make a gas, you don't make a precipitate, you really have no reaction. Because if everything is soluble, reactants and products, really all you have are a whole bunch of cations and anions floating around and nothing combining to make anything new. So we've kind of written a new product here, potassium sulfate, but it's not really existing intact as potassium sulfate. It's soluble. So it's really existing as the potassium and sulfate ions floating around. There's really no real product. So you need either a gas or a precipitate or water in order to drive this reaction to really make a product, a new product. Almost done. So there are some common formations of gas that I want you to be familiar with. One of them is if you begin with a sulfide, okay, you tend to make hydrogen sulfide gas. This is the smell of rotten eggs, by the way. You don't need to know that for the test. I just thought it was interesting. Okay, if one of your reactants is a carbonate or a bicarbonate, so this is potassium carbonate, this is potassium bicarbonate. If you have either of these to begin with, one of the products is going to be carbon dioxide. Forget that, you don't have to do this sulfate one. That's not very common. Okay, so if you have ammonium as one component in a double replacement reaction, one of your products is going to be ammonia. So there's usually only one multiple choice question that's a gas evolving reaction, and they won't be free response or not that common. So this is a little bit lower priority. I'm not saying blow it off, but don't give it the same priority as your solubility table or solubility rules and strong acids and bases. Here are some specific gas forming reactions. So for example, the multiple choice question I give you might show you these two reactants and say, what are your products? And hopefully you would say, well, it's a double replacement reaction. And hopefully you would notice that there's a carbonate in there. And you're like, aha, CO2 is going to be one of my products. Well, first you have to go through the motions of doing the double replacement reaction, which means the two outer ions combine, give you calcium chloride, and the two inner ions combine to give H2CO3, which happens to be called carbonic acid. Okay. Now, if you got this far, you would get half credit. But what you need to know then is anytime you make H2CO3, it automatically breaks apart in water to give you more water and CO2 gas. So another way to write this reaction would be calcium carbonate plus HCl. By the way, calcium carbonate is marble or chalk. They're the same thing, believe it or not. So you may know if you have marble and acid rain, that's what's causing our statues to degrade over time, is acid rain comes down and actually reacts with the marble and disintegrates it. So the products of these, you could either go through this two-step process I showed you down here, or you could just write directly that your products would be calcium chloride plus CO2 plus H2O. Alrighty. Here's another example. It's carbonate. This is actually bicarbonate, but you have a similar thing. So you combine the outer ions, sodium and bromide, and then combine the inner ions. Okay. When you combine HCO3 and H, same thing, you're going to get H2CO3, which is going to spontaneously decompose to give you water and carbon dioxide. So in all likelihood, the multiple choice question I will give you for gas forming reactions will either be something containing ammonium or something containing a carbonate. So you need to be able to do these two. Go ahead and try these on your own and see if you can predict the products. Now, what you would do if you're doing this on your own, you would say, aha, there's a carbonate. One of the products is going to be CO2. And here, hopefully, you'd say, ah, there's ammonium. One of the products is going to be ammonia gas. So let's predict the products for this first one. Don't worry about the CO2 you know is going to form yet. Go through the steps of the double replacement. So let's combine the outer ions. So we're going to combine hydrogen, which we know always has a charge of +1, carbonate, which is one of the polyatomics you need to memorize, has a charge of -2. So the formula for hydrogen, well, it's carbonic acid actually, is H2CO3. And the other product is combining the inner ions. Don't carry these subscripts over necessarily. Okay, the formula is going to be determined by crisscrossing charges. So sodium has a charge of +1 as an ion. Nitrate is another polyatomic you need to know, has a charge of -1. So those combine in a 1-to-1 ratio to give you sodium nitrate. So here are your two products. So let me rewrite this whole equation. All right. Carbonic acid and sodium nitrate. First you want to ask yourself, is this balanced? Hopefully you can see that it's not. We have 2 sodium on the reactant side and only 1 on the product side. So I'm going to put a 2 here. So by doing that, we now have 2 NO3 groups on the product side. So I need to also put a 2 here. And I think you'll notice now it's balanced. All right, so you get half credit for that, but then you have to remember that carbonic acid spontaneously dissociates in water to give you H2O and CO2. So the full balanced reaction actually looks like this. That's it. That's the balanced molecular equation. Okie doke. So now let's do the other gas forming reaction. Okay, again, ideally, I'm hoping that you'll see this NH4 and put off to the side that you know one of the products has to be NH3. All right, let's go through the steps of a double replacement. Combine the 2 outer ions, assign charges and crisscross. Ammonium is a polyatomic you need to know, and so is hydroxide. They both have same but opposite charge, so the formula, they're going to combine in a 1-to-1 ratio. Formula is NH4OH. That is one of the products. Then combine the inner ions, putting the metal first. Sodium, we've done this a million times, right? So sodium chloride is the other product. Let's write it out and make sure that it's balanced. And yes, it is. Okay, don't need to do any balancing. But what you do need to remember now is that similar to carbonic acid spontaneously decomposing, ammonium hydroxide also spontaneously decomposes into water and ammonia gas. That is it for the lecture on double replacement reactions. It's getting pretty complex. At this point, you've kind of tied together everything you've learned. I could give you names for reactants instead of showing you formulas. You need to know how to name stuff. You need to know how to write formulas for ionics. You need solubility rules, net ionic equations, double replacement procedure. There's quite a bit of practicing. So please, please, please do as many problem-solving practice as you can.